Hello, this is Peter Foy, Senior Technical Marketing Manager with GigaDevice, and welcome to my series on embedded MCU design. Good day, I'm Peter Foy with GigaDevice. I'm a Senior Technical Marketing Manager here, and today we're going to use Embedded Builder, the Graphical Configuration Tool within Embedded Builder to implement an ADC with a DMA. So let's go ahead and get started. So Embedded Builder is a free tool that we provide to our customers. You can develop no matter what device family you're using, if it's ARM-based or if it's RISC-V based. So we support all of our device GD32 device families within this Embedded Builder tool. Today we're going to concentrate on the Graphic Configuration Tool to implement the ADC design. And after we finish with that, we'll use a code generator to generate HAL firmware libraries based on the selections that we made in the Graphic Configuration Tool. Again, to date, the tool supports the E230 and the F3X0 series of devices, with more to come. So this is a screenshot of the Graphic Configuration Tool. There is a pinout tab, which is what's selected right now. There's a clock configuration tab, and then also a configuration tool. So based on the modules you select here in the pinout, they'll be available in the configuration tool. So we'll see that in the when we actually fire up the tool here in just a bit. So today we're going to be using the F310 series of device. It features a Cortex M4 processor, a flash RAM to 128 and 16K respectively. Today we're going to use one of the two UARTs and also the 12-bit ADC. There are 16 channels that you can configure for use. Today in our design, we're only going to use one. So let's take a look at the block diagram of the ADC. So you can see that you have 16 channels available for the input to the ADC. You also have 3 internal references that are available as well. You can select from a set of triggers that can be from timers, an external pin, as well as a start of conversion bit as well. So there's also channel management here. From the channel management, you can produce an end of conversion, which will be passed to the interrupt generator, or you can create a DMA request. So there are 4 different modes of operation. Today we're going to use the continuous operation mode, but there's a single operation mode, a scan operation mode, and a discontinuous operation modes that are supported as well. So you can see in the continuous operation mode that we have a single channel coming in here. We trigger the routine, and then as the conversion happens, there's in a conversion bit that's produced. So you can see you have a sample phase and then the conversion phase, and then when it's available after the conversion. So in this continuous operation mode, there's a couple of different modes. We're going to use a DMA channel to transfer the converted data. So there's a set of steps that are included to do that. So there is an ADC control register 1, and there's 2 bits in there. So there is a continuous mode bit that needs to be set and a DMA bit. And then we need to configure the routine sequence register with the analog channel number. Next, we need to configure the ADC sampling register. So there's 8 different settings there for the sampling time register. Then there's also 2 more bits that we need to set in the ADC control register. And those are the external trigger enable for routine sequence and the external trigger select for routine sequence and the ADC control when register. Next thing we need to do is prepare the DMA module to transfer data from the register, the ADC register, that will house the data after the conversion is complete. And then we'll need to set the SWRCT bit, which is a software start software conversion bit to generate an external trigger for the routine sequence. So this is a shot of what the actual board looks like. So we're going to use the UART 0 from the IC to USB, and there's a couple of pins there we're gonna utilize. So for the transmit, PA9, and for the receive, PA10. You can see there is a rheostat or a variable resistor here hooked up to ADC N2. So that's the channel we're going to use for the ADC. And then we're also going to use the debugger to interface to the design itself. So that's where the GD link is included on the board itself, so you don't have to buy an external piece of hardware. So all of our eval kits and starter kits include the GD link debugger. So let's go ahead and fire up Embedded Builder. Let's configure a workspace. Launch the tool. So this is what the tool, the splash screen shows up when Embedded Builder comes up. So we can create a project. Again, within the tool here, you can import projects. There's a user manual for Embedded Builder. As well, the data sheet is available for the device we're using. So the F310 is available here. A user manual's available here as well for the F3X0 family. And then there's demo suites of software that I would suggest that you download and look at as well. So like I said, the F3X0 family is available for all the data sheet, demo suites. There's also a firmware library available for this device as well. So I would suggest that you download those and take a peek for reference. But we're going to go ahead and create a project. So let's just give it a project name. And then again, we're using a series, the F310 series. And this is a device that's on the board. It's got 64K of flash and 8K of RAM with 39 I/O pins. Okay, so this is a graphical configuration tool. And the mode that comes up initially, or the tab that comes up initially, is a pinout. So it's in alphabetical order. So the first thing we're going to do is we're going to select the ADC. And again, the ADC that we're using is the input 2. That's what was available, or the rheostat was connected to the ADC N2, and that's connected to the PA2 input pin. So the next thing we need to do is we need to configure the system. So move that over too far. So we're going to actually use the serial wire for the debugger. So we need to select that for debug. And then as well, we need to configure the RCU. So there's a couple of crystals connected to some I/O pins for the high speed clock, and then also for the low speed clock. and those are the pins on the device for the high speed and low speed clocks. So we have everything configured here except the UART that we're using. And we're using USART 0. And we're going to use it in asynchronous mode. And then it's selected by default PV7 and PV6. But if you recall, the pinouts on the device for the USART 0 that's on the board being utilized is PA9 and PA10. All right, so that is all we're going to use. We're going to use ADC input, IN2, and also the UART PA9 and 10, and then the debugger to these two pins. And then on the board itself, like I said, they're using oscillators, external oscillators. So that's all we have to do there. Next, what we're going to do is we're going to configure the clock. So again, you can use the wheel on your mouse and the control to zoom in. There's other methods as well. And I want to configure the clock at 12 megahertz for the ADC. So in order to do that, instead of using the internal reference clock, I'm going to use the external clock. And then we need to adjust this, I think, down to 3. That'd be 24. And then if we divide that 24 megahertz in half, we get 12 megahertz there. So, and then everything else we're going to leave as default based on that, that high-speed crystal input. So since on the pinout we selected the ADC and the UART, it shows up in the configuration tab. So first thing I'm going to do is configure the UART. It's going to be really simple here. The baud rate is going to be 115.2, and then the word length 8N1, which is typical of a UART interface. And then we're going to select apply here and then OK. So it was OK by default, so we didn't make any changes there. So next thing we're going to do is we're going to configure the ADC. So we're going to leave the data alignment the way it is by default. So at least 7-bit. And then we're going to leave the resolution at 12 bits. We aren't going to do any oversampling for this simple design. And then we're going to enable the routine sequence conversion, and we're going to give it a routine sequence length of 1. Again, we're going to use the start of software conversion as a trigger select. There are the external interrupt or the external lines available for that, as well as a suite of timers. We're also, if you recall, in the mode that we're utilizing this design, we're going to use it in continuous mode, so we're going to enable that. And then it already pre-selected channel 2 for the rank for the routine sequence settings. And then if you recall, we need to set the sampling time register. So I'm going to be a little more conservative here and set it to 55 cycles, just so it settles out and gives us a good reading. So that is all we have to do there. If you had, used more channels, that's where you would select the routine sequence length of a different number, and then all those different channels would have been shown up down here for availability to select in the rank setting. So next thing we're going to do is go to the DMA tab. Again, we need to add a DMA here. And it's not real obvious to me, but you have to go under DMA request, and then selected, you have to select ADC. And then you have a couple of different DMA channels available here. We're going to use channel 0. And we're actually going to, the direction is from the peripheral, the ADC peripheral to memory. I'm going to change the priority of that DMA request to high. We're going to select the mode to circular. And then for 12 bits, we're going to do a half word, which would be 16 bits available to put the data from the channel into the, or from the peripheral into the piece of memory. So we select apply here and OK. And that's the 3 tabs where we configured the device. And after we do that, we're going to go to project, and we're actually going to generate the code for this design from the Graphical Configuration Tool. Okay, so let's go ahead and take a peek and see what was actually implemented here. So again, you have your infamous main.c file. So we can see where the system initialization was done, clock initialization was done, GPIO was done. We also implemented a DMA channel, the ADC, and the UART. So if we dive down into the ADC itself, we can right mouse click on it, highlight it, right mouse click on it, open the declaration, and that'll go into this HAL initialization C function. So let's go ahead and start at the top. So there's an entity here called ADC info, and it's based on this structure. So if you hover over it, you can see what's in the structure itself. Same is true for the DMA ADC info. There's a structure associated with that as well. And then the UART info, there's a structure associated with that as well. So each one of these variables was defined here as a structure. And then, as you do the system initialization, it's going to set up the clocks and also the non-maskable interrupts as well. Here's where the clock initialization was done based on the settings that we made in the clock settings tab. And then the DMA is pretty simple here. The DMA configuration was done in the ADC. So all of that code is going to be in the ADC initialization. So the GPIO, it initialized all of the interfaces that we're using. So for the UART debugger and also the interface to the ADC itself. So let's take a look at the ADC initialization code. You can see where there's a variable here, the GPIO initialization parameter for a GPIO structure. It shows you where in that structure there's a mode for the mode pin. There's push pull, the speed, and if you using that pin as an alternate function. So you can see where that initialization parameter for the GPIO pin here, we're setting the mode, the type of push-pull, it's set as none, the mode for the pin set to analog, the speed set to 50 megahertz, and it's set to GPIO alternate function 0. And then we pass that parameter back to the initialization for the GPIO, and that's for port A, pin 2. So next we set the ADC structure initialization for the ADC parameter. So you can see where we set the data alignment. Remember, if we did that for the LSB, we set the resolution, scan mode, and then also oversampling. And then we pass that back to the ADC info entity. So the next thing we did is we did an ADC ADC configuration parameter. If you recall, we enabled the routine sequence conversion. We set it to a length of 1 because we only have one channel. We are not going to do an external trigger, so we set that to none. So, we're going to use the start software conversion trigger. So we enable the continuous mode because that's what we're using. And then we're going to pass that information for this configuration parameter back to the ADC. Next, if you recall, we set the routine configuration parameter, and then we set it to ADC channel 2. We set the sampling time to 55 points, and the sequence was set to 0. Again, we've passed those parameters back to the ADC info structure. Then the next thing we do here is we set the direction for the DMA. So we're doing the DMA initialization here, and also the device structure here as well. So we're setting up the ADC init parameter here, direction. We're enabling the memory, and then we're passing it from the peripheral to the memory with a size of 16 bits, and we're going to use the circular mode. And we set the priority level to high. Again, we're going to pass that parameter information back to the DMA ADC info entity this time. So all of that was done for us, but we need to do a couple of more things here before we can to set up the interface to the ADC. So first thing we need to do is we need to set the trigger configuration. Next thing we need to do is enable the ADC interface. Next thing we need to do is calibrate the ADC and reset it. Next would be enable the DMA function. And then finally, we need to enable the ADC software trigger. So where will we find these functions to implement this? I would go to the firmware library for the HAL peripherals, and I would go to the include file and then the header file for the ADC. So typically, you have all the register definitions. If you recall, we're going to need this ADC R data, which is where after the conversion happens, that's where that data is housed. After all these definitions are made for all the bits and everything else that's included in the ADC, the structures, etc., all of the functions that we're looking for are going to be at the bottom of this header file. So if you recall, we need the ADC trigger configuration. So right here is some ADC trigger configurations, and we actually need this HAL's ADC external trigger config. So that we need that. So that's the first thing we need to do. So we can just copy the whole thing here. So then you can either hover over it to see what you need, and these are the settings. So we're going to set it to the routine channel. If you recall, we don't have any inserted channels because we only have one, and then we're going to enable it. So I'm going to copy that. And then we're just going to enable it. So we got that. Next we need to do is enable the ADC interface. So that would be enable ADC interface. Right here we go. Then we want to do a calibration reset. But before we do the calibration enable, I would suggest that we put in a delay. And if you recall from our previous video, that would be in the system file. So, and I think that's at the bottom of this as well. So there's, copy that, base tick delay. Let's delay it by 1 second. Well, let's do it by 1 millisecond. That should be suffice. Do the calibration. And then we need to enable the ADC DMA function. And then finally, we need to enable the software trigger. All right, let's go back there. We can open decoration, and we're going to do the routine channel. All right, so I think that's all we need to do here. So like I said, we need to set the trigger configuration. We need to enable the interface itself. Then we're going to delay by 1 millisecond, calibrate, then enable the DMA mode, and then we're going to set the trigger to the routine channel. All right, so let's save that. Let's go back to main here. So we do need a global variable here. So That sounds like a pretty good name. So the next thing we need to do is we need to actually get the value of data from that DMA channel. So we need to do a DMA start, HAL DMA start. There's a couple of different functions you could use here, but let's do that HAL DMA start. Okay, so you can see that there is the DMA device structure information that needs to be passed into here. There's also the source memory buffer address. So the source memory buffer address, if you recall, was from the ADC RData register. If you recall, that was in the ADCC. I'm sorry, the header. So at the very top, we had the RData, ADC RData. So now we need that. And then we're going to use our ADC value register. And then I think what else was needed here? Oh, the length was the last parameter. So we need this DMA device structure information passed, and we already set that, and we'll find that in a second. So the length we're going to set to 1. Okay, so where are we going to find that DMA device structure information? So if you recall, whenever the initialization was created at the top of the file, whenever we were reviewing it, this DMA ADC info structure was created here. So this is what we need. So we're going to copy that. And we just need the address of that. Then the only thing we need to do is basically smythe the RData and the ADC value, pass type. What type are we going to pass to it? Need to pass it the address. Same with the ADC value here. All right, I think I got all that set right, so that should be right. So the device structure for the DMA, the source address, the destination address, and then the length. So that looks good. So the next thing we're going to do is we're going to print this out. I'm going to cheat here. Copy this code over, since there's really no value right here. So I'm going to delay by a second, print a couple of things out to the UART, And then we're going to print the regular channel data, the ADC value, and then we're going to set the value back to 0 to make sure every time we circle back through this code, we're doing the same thing. So the other thing that we need to do is for the printf, we need to redirect that library printf function to the USART. So there's code, and that code is included in the manual. So you can get that code in the manual. I'm just going to go ahead and drop it in here. So again, we're just going to redirect that printf function to the USART. Here's the code to do it. I won't explain it, but here's the code to do it. Again, you can find that in the manual for the software. So I think that's all we need to do here. So I think we're done there. ADC value initialization. We can go look at the ADC initialization code again. Everything looks good there. We trigger, set the trigger, enable the interface. We calibrated the ADC. We enable the DMA, and then we set that software trigger as a routine channel. And we basically started the DMA. And then after we do start the DMA, then it's automatically going to put that value in this from this register into that ADC value. All right, so let's go ahead and save this. Then we'll go up here and we'll compile this. So go ahead and build the project. Let's see what happens. So that looks good. So let's go ahead and debug. Set up debug configurations. Double click on the debugger. It automatically detects that there's a debugger on the board. So here we go. Let's go ahead and select debug. It's going to switch perspectives on us. Okay, it comes in an initialization code, and I'm going to set a breakpoint right here. So the other thing that you have access to are the registers, right? So you have your 16 registers available, stack pointer, etc. here. The other thing that I like to look at when I'm in a debugger, if I have problems or something, is I want to look at the peripherals themselves. So kind of hidden here in embedded builders, but you can go to Window, Show View, select Other, and then under Debug, we can select the peripherals view here, and then all of the peripherals are available here. So we're in particular looking at the ADC. So we can see in the control register where those bits were set that we needed earlier. So let's go ahead and take a peek at that. So if you recall, in the ADC control register 1, we needed to set a couple of bits here. So the first thing we need to do is make sure we set the DMA bit, and we hadn't. So that should be set here. The CTN bit, continuous mode bit, should be set here. Maybe it hadn't read it yet. So of course it hadn't read it yet. We hadn't got to the breakpoint yet. So it just went into the startup code, if you recall, and it stopped right there. So let's go ahead and run it until it gets to this delay here. And it did. So now we can go back to peripherals view, and we can see where that is no longer, the control register 1 is no longer set to 0. So again, we have the continuous mode bit is set to 1. The DMA mode bit is set to 1. So you can see where all the bits that we needed to set earlier, the trigger enable for routine sequence, all those are now set. So if we open up our serial port, select OK, then we need to set that serial port up to 115.2. All right. All right, so we're getting a different, the ADC channel data is showing up here at the UART on the output. So that all looks good. I'm going to toggle the breakpoint here, go back, and then I'm just going to go ahead and continuously run this. So I'm actually going to grab the rheostat on the board and change the setting on the rheostat. Okay, that looks good. So that, I think, is all I wanted to show in this particular video. Anyway, we set up an ADC to use a DMA mode, and there you go. I'll try to post this code up under the YouTube video. Anyway, thanks for joining me, and have a great day.